All right, so I hope this works because I made two videos and I think I had the microphone off. Too bad. So I just made one up on the fly here because I'm heading out the door soon, and I thought I'd ask some questions that we just dive into a few of them a little more deeply. So I think I got like 20, I don't know, 22, 23 problems, something like that. And then I think I'm going to give you a little assignment, a little problem to work on, a little curve sketching. And because it gave me a little pause. And so I started thinking about it. How would I go about getting a good feel for what a graph looks like? Um, and so I'll talk about that at the very end of the little video here. So we haven't done an approximation in a while. So how about you approximate the fourth root of 16.1? See if you can do it in your head. It's good, always good to do some mental math. So see if you can figure it out and just write an answer. And I'll try to do the same while you pause the video and go for it. So I'm looking at 1/4, 16 to the minus 3/4. 1/32, 1 over 320. I'm going to say it's 2 and 1 over 320. Let's go find out. So I'm going to use 16. And if I take the fourth root of 16, I get 2. So I can write that. And I'm going to rewrite 16 to the 1/4. I'm going to take the derivative. I'm going to put 1/4 in front. Drop it down 1, minus 3/4. Fourth root of 16, 2 to the negative 3, 1/8 over 4 times 4 is 32. So I got that right. And if I drop 16.1 in here, I get 1/10. So 1/10 times 1 over 32 plus 2, I'm sticking with my answer. All right, that's a good start. Because when I do the washer method here, I just made one up for rotation in terms of y. I thoroughly expect to botch that, but we'll see. Haven't done it in a long time. All right, now this one here. I think you should draw the cosine curve from pi over 6 to pi over 4, look at it, and estimate the area. And the reason I do that is from Algebra 1 up to trig, I have students memorize, and we do this kind of find the cosine of pi over 4, find the cosine of pi over 6 in Algebra 1. And people have some pretty good success with it. And that way we get to work with it at Algebra 2. And then in trig, at least in my classes, I have to teach the Algebra 1 to trig class to every single level. Algebra 1, students who have had Algebra 1, I still do it at the Algebra 2. And the pre-calc kids, I definitely do it for. You got to have all this algebra skill and trig, certain amount of trig skill in order to tackle the calc. So very similar lesson sets for those students. So go ahead, you pause the video. I came up with, I think about 0.17 was my area. So you have to know these values. So we're gonna, and I'm not doing the fundamental theorem. I'm gonna draw this first. There's the first period, pi over 6. Where do I put pi over 6? And what does it mean? That's why I'm having you do this, so that if there are any gaps in your foundation, we gotta talk about it. So pi over 6, 3.14 divided by 6, I'm estimating to be 0.52. So this thing is at 90 degrees, so that's 1.57, roughly, pi over 2. So 0.52 would be about a third of the way there. So that strikes me as being there, 0.52. And pi over 4, 3.14 divided by 7, I'm calling 0.78, I think. So I'm going to call that 0.78, which is about halfway. 0.78. Yeah, double that. You're pretty close to that. So we have a very narrow strip. All right, so you need to know what the cosine is at pi over 6. Well, that's 0.5. All right, cosine of pi over 6. Breaking this up into 6 parts. Oops. Yep. No, cosine of pi over 6, excuse me. I want to be over here. So this is, boy, yeah, this is not left to right, right to left. Ooh, I'm glad I'm doing this. So that's a half, right? And that's root 3 over 2. So at pi over 6, which is the 0.52 one, I was doing the wrong one there for a second, is root 3 over 2, which is about 0.87. Okay, so I did look at this, and And I played with it, doing the drawing that I'm doing right now. And then this one at pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2, which is 0.71-ish. Right, so I like to have those memorized. I think you should too, or I wouldn't be having you do this. Very close to a trapezoidal rule. Trapezoid's going to underestimate a little bit. So it's going to underestimate. And for the trapezoidal, that's what I got for the trapezoidal. So this area is going to be a little bit bigger. And so I decided to do 0.52 to 0.78, 0.26, and cutting that in half, we'll call that 0.79, something like that. 8 down, 8 up. Yeah, 0.79. That's a different one. I think I did 0.78 before. So let's see what this gets us. That's a 5. That's a 4-2 with a 5 is a 7. Carry the 4. Let's see, did I do that right? It's 42, 47. Yep. 2 9's 18. 2 7's 14. 1's 15. And so that's 4, 7, 4, excuse me. 15, carry the 1, there's a 0 there, there's a 2. So 2, 5, 8, so that's going to be about 0.2. And I think when we do the fundamental theorem, we can get ourselves a little bit of an estimate and see if you remember any of the values that I just quoted. Right? Because this is going to be the sine of pi over 4 minus the sine of pi over 6. Pi over 4 is about root 2 over 2. Well, it is root 2 over 2. And that's about 0.71. Sine of pi over 6 is 0.5. It's a half. 0.21. Trapezoidal rule estimated 0.2. I mean, these are rough estimates. But it's really important to have a sense of size when you're working with that. Does my answer make sense? Can I trust it? When you're first learning how to do these problems, you really want to take the time to dive in numerically. Say, is it making sense? Sure seems to. So let's get rid of that one. So yes, I think you should know. If not, make a little journal entry. Just put it on a piece of paper. Root 3 over 2. 0.87. Root 2 over 2. 0.71. Square root of 3. 1.73. Square root of 2. 1.41. Just write them out. Flip the page, look at it, takes you 5 seconds one night, 5 seconds the next night, 5 seconds, and then you don't have to flip the page by the 4th night. And you're working with these numbers consistently. You should have a feeling for size. All right, next question. There's my ramble. All right, so let's get into the area, just the calculations now. We're looking at the cube root of x. Cube root of x looks like this. Very similar to the square root of x on the right, but you can take cube roots of negatives. Y equals 2. That's this height right here. All right, that's going to be that height. At x equals 0, this is a border. And I want to rotate this around the x-axis. So all I'm doing is rotating around the x-axis. So I really don't need this except for 0 to what? A height of 2 occurs at a width of 8. All right, so what's the calculation that gets me this area right there? Well, that area is the integral from 0 to 8, the cube root of x, dx. That's it. Now, how would we do it in terms of y? Well, in terms of y, I've got to go from here over to here, which means that this x distance is being taken away from the longer x distance, okay, in order to get me that differential. So it looks like I have to do 8 minus that x distance. Now, if I have y equals the cube root of x, then I think that distance x is y cubed. So if this y was 2 and I cubed it, I'd have 8 units. Oh yes, I do. I have 8 units. But as I move to the left, these distances are getting smaller. So how does that happen? Well, boundary on the right minus the boundary on the left, dy from what to what? 0 to 2. You're pausing the video as you're trying these things. All right. Now, what would happen if we wanted to rotate that area around the x-axis? Well, that's when we had that disk method, right? Let me get a disk. Obviously, I haven't prepared too much of this, or I would have had this more handy. So we have a disk here, one slice of the loaf of bread, and we're going to add up a lot of slices, and from right to left, those slices are getting smaller and smaller and smaller until they disappear. Okay, so what's one slice if I'm rotating around the x-axis? Well, it's the same thing we had before. It's the cube root of x. And what do we want? We want a pi r squared in. So I bring the pi out, and we'll square it with respect to x. And how are we going? From where to where? 0 to 8. And that's going to get me something that looks like this. Right? Kind of a, I don't know, whatever you want to call it. Some kind of cup shape. Right? With an infinite number of these disks. And the disk has a little bit of area as it rotates and a little bit of thickness. And there's your thickness right there. Okay, so that's that. If I stumbled here at all as I'm talking to you and I make a careless error of some kind, conceptual or mechanical, let me know. Let me know, because I'm just kind of marching through this. Now, I haven't done this one in a long, long time. Rotate around the x-axis, we just did those three. Now we're going to rotate around the y-axis. And that's why I have x equals 0 here. So there's your y-axis, there's your x equals 0. We've got our y cubed now, everything's in terms of y, we don't have to talk about that again. And over here we have 8. So I'm rotating this area, kind of like a propeller, right? With a lot of empty space here. So we're going to actually have to take away that rotation and bring this. So we have a big R, that's my big R, 8. That's a fixed big R. That's going to show up over here, and I'm going to get something that looks like this on this side, and it's going to... All right, so I got a big R, which is 64 when I square it, and I got a pi here, and I'm going to go from 0 to 2. That doesn't change. But I got to get my little r squared, and I got to get that out of here. And of course, it's going to be in terms of y. So what is this x distance? What is that x distance? Well, it's a function of y. It's y cubed. So what do I have to do to y cubed? I gotta get a little square going there. Right, this was 8 squared. And they call this the washer method, kind of like a donut. You know, you get a hole in the middle. Okay, and I think that's it. But I haven't done one in a lot of years, so I don't remember. If I made a mistake, that's why we're doing it. So we can learn from it, learn from your mistakes. Hopefully I didn't make one. All right, so now we got f of x, little f of x. I think you can see this. I'll move it down here a little bit more. Little f of x minus 3 to the 5th, x plus 2 squared, x minus 7. How many points of inflection does big F have? How many points of inflection? Okay, and this is a first derivative. Try to find out using the first derivative. Let's plot the first derivative. Let's graph it. Not plot it, but sketch it. I guess I can use the word plot, but that seems to be more of a put a number in, get a number out. So, positive 3, odd exponent. It's going to change signs. 4 makes a positive, 2 makes a negative, but doesn't affect these parentheses. Negative 2, no sign change at negative 2, sign change at 3, sign change at 7, because that's to the first power. Put a big positive in, getting a big positive out. 7 is a linear through the x-axis. 3 is a fifth root. Oh boy, that's going to look like that. And then we got something like that. So, how do you determine concavity using the first derivative? I hope, if you've done all the other lessons, that you can answer that question. When the first derivative is decreasing, my function, big F, is concave down. When it's increasing, it's concave up. So when do we make a transition from down to up? One time here, down to up, twice. Down to up. Okay, it's flat there. So 2 points of inflection for big F. When is big F decreasing? Big F is decreasing when the first derivative, this is the first derivative, this is a 1, first derivative. When it is negative, so when x is less than 7 but greater than 3, big F is decreasing. Okay. Get some space. Let's do a little y prime for number 5 over there. Can you see it okay? Let's bring it back this way. All right, what do I see for y prime? Well, we'll do it right here. I see 12. 4 times the 3, sine. Drop it down 1 with respect to where I am on the axis, and that's going to come from the sine of e to the 2x. Boy, I don't have room for it here, so let me just do the rest of it out, and you can check your work. You know, y prime is equal to 12 sine cubed e to the 2x cosine e to the 2x times e to the 2x times 2. Wow. So I did the derivative of a fourth power. Yep, dropped it down 1. I did the derivative of sine, which is cosine. That came next. That was the second chain. Then I have to do e to the 2x, which is its own derivative, times 2 because of the chain. All right, can you use a limit? Let's use 2 limits to describe f prime of a. Stop the video. What's f prime of a? Well, it's f of x minus f of a over x minus a. Didn't leave myself enough room. It's that limit as x approaches a. That is f prime at a. There's your y2 minus your y1 over your x2 minus your x1. As x approaches a, I have a, and I have a plus 0.01. So that becomes my dx in the denominator, and we compare it. All right, when I plug that a plus 0.001 right in there, yeah, got a couple of points really close together on a curve. Got to see what we get. The other way to do it was to look at f prime of a is equal to f of a plus h minus f of a all over h. Remember, a was some number, a plus 0.01. What happens when you subtract these? That minus a, the a's cancel. You get your dx that way, which is just a little horizontal shift from what a used to be. And then I evaluate where I am with respect to those x values. And I do a little comparison. y2 minus y1 over x2 minus x1. All right, that's h, 0.01. Now maybe that's coming into focus for you a little bit. Maybe you're starting to see that. Now I can't integrate cosine m squared dm. So we're trying to do the integral of sine x, x cubed, cosine m squared dm. I can't integrate it, but I can still find, if this is big F, I can still find little f. Do you remember how? We drop it in. If we drop it in, we have the cosine of x to the 6th times the derivative of what I drop in times 3x squared minus, I dropped it in, I get the cosine of sine squared x, ran out of room here, times the derivative of sine, which is cosine. Okay. Sorry, I ran out of room. So let me come over here and start working here so that you have a problem below. that I can work above. So you're trying to write the equation of a tangent line if given dy dx equals minus 3x plus y over x squared and y of 2 equals 3. Well, if y of 2 equals 3 and I'm writing a tangent, you're pausing the video, but I certainly can start here. It's always nice to get started. You get stuck writing a paper, right? What do your English teachers tell you? Get that first sentence down and go from there. I think that's what they say. I don't know. It's been a long time since it's been in an English class. Well, what is dy over dx? Tells me my slopes and my tangents. Well, there's a formula, and that formula requires an x and a y. I have an x. I have a y. So I'll plug 2 and 3 in. Minus 6 plus 3 is minus 3 over 4. That's the tangent to whatever curve y is, which we haven't looked at, obviously. Okay, so that's that problem. All right, can you change the limits of integration? Haven't done that much at all. All right, can you change the limits of integration and fill in the boxes? Well, you got to pick a u, right? I'm seeing u as 4x cubed. So it looks like this is an e to the u problem. And I know that du, skip a step now, I hope, 12x squared can be written for dx, so I want 12x squared. I don't want 7x squared, so I guess I'm going to have to get rid of the 7 and bring in a 12. So that would have been here. So this would have, I guess I've got to do it here. So I don't want that 7, I want a 12. I'm sorry, I got that backwards, right? The 12x squared is going to divide into this, the x squared is, so I want 7 12ths. Because 12 should show up. So there we go. Yeah, I've lost my train of thought, but it's back again. So I want 12x squared, I don't have it. So if I put 12 there, then if it's not there, then it must have been divided out of the problem, and I brought in the 7. Boy, was that awkward. All right, so 7 12ths. Doing that here. Okay. Now, if x is 1, when I do u, when I put a 1 in, my bottom limit's 4, and my top limit is when I put a 2 in, and when I put a 2 in, it looks like it's 32. 2 cubed, yes, 32. So that goes here. And then I've got this. And that's easier to do. Saves you a little work. All right, so that was that. All right, little quotient rule. 4x sine of 3x. And the reason we keep doing it, just like flashcards, you got to be able to remember this stuff. You got to have working knowledge. And how do you get working knowledge with anything? You work with it. So we're working with a quotient rule. So y prime is equal to low sine of 3x. D high times 4 minus, dot there, probably put the 4 in front, but that's all right. Low, d high minus high, d low. The derivative of sine of 3x is 3 cosine 3x. All over low, low. Sine squared 3x. And there's your quotient rule, little practice. Can you take the derivative of x times the 5th root of x? Oh, come on, board, behave. Or I'll erase you. Oh, sorry. Well, you want to make sure you know from your Algebra 1 days that 5th root of x could have been written as x to the 1/5. And the rules of exponents means that y could have been written as 5/5 plus 1/5 is 6/5. Well, that's easy to take the derivative now. So we have 6/5 x to the 1/5. Okay, taking down 1. Okay. Next, can you take the derivative of y equals 2x times the secant of 3x. Okay, so length times width. Derivative of that is L prime W plus W prime L. Go and look at the product rule in the playlist and you'll see the numerics as to y. And you'll have the shapes drawn. Draw that rectangle and play with it. So y prime. Take the derivative of the first factor, which is 2 times. Leave the second one alone. Secant of 3x plus. Leave the first one alone, but take the derivative of the second, and I'll do that first. No, I'll do this one first. So leave that one alone. Oh, I think I got to get more space here. 2 secant 3x plus, leave it alone, 2x times the derivative of secant 3x, which is secant 3x tangent 3x times 3. Chain rule. Got to take the derivative of what's inside that parentheses. One more problem, and then I'll give you a little challenge to work on till the next video. So what's the limit as x goes to -4? And notice I put a little symbol there, a little negative symbol, which means it's a one-sided limit. We're only heading to -4 from the left. We're going to go to -4, -10, -9, -5, -4.01. And if I add 4 to that, I've got -0.001. Just get a feeling for it numerically. And if I put -4 into the numerator, I'm near, it doesn't have to be too close, but I'm near -11. Well, I think that negative into that negative makes it a positive, and I got a feeling 0.001 I can put into 11 a lot of times. So this answer was positive infinity. Now I was wondering what y equals x to the 4th minus 2x look like. Right? And I really thought about that for a long time. I thought about it from factoring the difference of two cubes, which I'm going to do in this, even though you don't probably see them yet. Yeah, going to factor the difference of two cubes. And that got me well, I'm not going to give you any clues here. Okay, so I'm going to hush up. Use calculus. Do not plug 1 in and go, oh, 1 gets me such and such. See if you can estimate what the roots are. How many are there? There are 4 roots. Okay, there could be 4 real. They could be 2 real, 2 imaginary, or they all could be imaginary, right? But the polynomial, right, the big exponent of those polynomials always tells you the number of roots that you have. All right, so play with it, see what you come up with, and I'll go through it with my mindset. We call it curve sketching, so use calculus to analyze that. See how close you can come up to what it looks like and answer some questions around concavity, rates of change at instances, things like that. All right, so that's the first thing I'll do on the next video. And I hope that I have the microphone on now, because I just wasted about an hour and a half on 2 videos, which I'll have to do over again. All right, I'll upload this and little practice, as Alvin Iverson would say. Allen Iverson, yeah, practice.